Hello everyone, my name is Yogesh Punia, and today in this episode we shall be expanding our discussions further in the concepts of that we should know while dealing with the field that's called electrostatics. What we have learned right now is that we have the electric flux concept, we also know the electric dipoles, how do they behave with each other, and if I have got some point in their vicinity, how will they affect it, and if I place the dipole in some electric field, there will be some torque acting over it that will try to align it in the direction of electric field. What is the physical significance of the dipole? Now, can you point out a very similarity that lies all the concepts that we have discussed so far? Yes, what we have discussed is that we have taken singular charges, that is we had some say positive charge, then we had a negative charge. Then we moved on and we have said, okay, we have got two charges separated by a certain distance, they are equal in magnitude and they only have their different what you call positive charge is there and negative charge is there. But is this the case everywhere? Means can you always find some discrete charges and pick them up like this? This is the positive charge, this is the negative charge, I got them too, I formed a dipole. Well, obviously this is not the case. So we must find a way to also consider a very good aspect of the nature, that is everything is continuous. We know about the discrete nature, but we also must also know about the continuous nature of the substances around us, and henceforth the continuous distribution of the charges into the things that we consider. So what is all about the continuous charge distribution exactly? Suppose I have got two charges, some is plus 1, one is minus 1, and also there is q, that is a unit, I must take that into consideration. So I have got some plus q and I have got some minus q. Thing is absolutely fine, because I can simply find out the Coulombic force, or I can find out the electric flux, electric field, anything, and even I can find out the torque. But is this the case always? No, means I cannot always pick out single charges stating they are plus q, they are minus q. What I can see is that I can have a pen like this and I can say that there must be some positive charge here, but there can also be some negative charges here. Means I am not sure about it. So simply stating that this is the positive charge and this is the negative charge is nothing but I am trying to make it somewhat mathematically simple, because we want to live in a world of ease. So we should have some simpler mathematical treatment. But after going through the ladders of say A, B, C, D, we must know how to form the sentences. And when we form the sentences in the field of electrostatics, we say that now since we have considered the discrete charges, there could be somewhere some of the continuous form of it, and then we say, okay, we are going to study the continuous distribution of charges, that we go for this. Now for an example, if I take this pen into consideration and I just wanted to know that what is the electric field due to the charges here, what I must consider is that I cannot know where exactly the electric charges are. I can only say they can be here, some of them may be here, some of them may be here. That is, I am going for the continuous distribution of the charges. But if I keep on looking into each and every charge, my life is really terrible. I will get tired of it, but I won't get the hold of it. So what I will do is, I will have a clever argument. I will say that since the charges are always there, I will try to cut it into equal parts. And so I will cut, say suppose this is the part that I am taking into consideration. I will cut this pen like this. So I have got this part. Now you must remember the concept of electric flux. Yes, correctly, this area is a very important part of it. So this is the area, there is some electric field, So there comes out some electric flux. And the direction is given by, yes, the direction is given by the normal to this area, and the flux is simply phi is equal to E dot delta S, which is E delta S cos theta. Theta is the angle that we are considering. So this is the continuous charge of distribution if I consider this pen. If you find this pen to be something very big, you can always go for some lighter objects or some thinner objects. Just as you can say, okay, I've got a thread and I'm going to divide the thread into equal parts, and then I will calculate the charge due to each and every part that I am considering. So what happens is that if I have got a part, say suppose its length is delta L, so I will go for the linear charge density of it, because as we have considered in the case of electric flux, what we have considered is that the area that I am taking into consideration will affect the electric field lines to come out of it. So in another way, it is the density. So that same density comes into play here. The linear charge density is nothing but, if I am considering a thread and if I divide that thread into equal parts, what will happen is that say suppose the delta L is the length of this thread. Suppose this finger is the length of this thread from here to here. So there must be some charges residing over it. That is, say suppose delta Q is the charge and delta L is the length of my finger, that is the string. What will happen is that the linear charge density will be lambda equal to delta Q by delta L, where delta Q is the charge on this length and delta L is the linear element. If I want to go for some more of it, I want to have a more of it, and I say, okay, I agree with you, but I want to have this experiment over some, say suppose some cardboard, or I've got a box and I want to find the continuous charge distribution, or how will be the distribution of charge over that box. Well, thing is really very simple. Likewise, we had delta L, that is the length that I taken into consideration in case of linear charges. What I will do is simply, suppose this is the pen, and just consider it for the sake of physics that it is some sort of rectangular box. I will simply cut it. So what I will get is, I will get some rectangular boxes, smaller rectangular boxes, and then there will be some charges residing over the area of those smaller boxes. So what will happen is that there will be some surface charge over density. That surface charge over density will deal with the charges that are residing over that particular area. So if I denote the surface charge over density by say sigma, so sigma will be delta Q upon delta S, where delta S is the surface charge element. Actually it is delta is the surface element, but since the charges are taken into consideration, I call it surface charge element. Likewise, if you have got a three-dimensional figure and if you say I want to know that of a cube, well, that can also happen. Only change will be that it will be some cubical charge or distribution, and then I will go for the delta Q charge over it, and then I will find out what is the volume of it, that is the volume of the smaller part, that when I cut it into some equal parts. So I will take a simple part and I will say, okay, this is the part here, the volume is like this, and there will be some charges over it. So there will be some charge density, it is delta Q upon delta V. Actually it is that simple as it. But sometimes I get really very annoyed with this. Means I have got so many charge distributions and someone tell me, okay Yogesh, you need to divide it into equal parts, and then what you have to do is you have to take one part into consideration. You find out the linear charge density or the surface charge density or the volume charge density. That depends upon what thing I am taking into consideration, that is if it is a thread, if it is a square sheet, or if it's some sort of metal cube. It is really very annoying because I have to count each and everything. Well, there is a rescue, and the rescue is that you have to simply go for the charge distribution due to one of the part that you are taken into consideration. That is, you simply get a part and then you say this is the linear charge distribution due to this one, and since this part is equal, means I have divided the whole element into equal parts, I will simply add up these things. If it is really very long object, like a very long thread, and you don't know how much parts you have done, so you will say, okay, I will simply sum it over all the parts and I will get the total charge distribution over that thread. Likewise is for the square sheet, and similarly we can have that for the metal cube. But since we are physicists, we always wanted to let people know that this is the concept of continuous charge distribution, and if you want further explanation, we can give you something more. But what more we should give them? Well, to our rescue, we have got an analogy that is in the form of mass. Well, you all know mass. Yes, mass is a very simple concept to understand the distribution of charges. For that, we must go back to our school days and we must know mass is something that is the quantity contained in a body. So, if I have got some body and if I divide it into some parts, so the mass of one part will be equal to the mass of other parts, since the parts are equal, and when I sum them up, I will get the mass of the whole body. In this way only we can understand the concept of continuous charge distribution. That is, if I have got a very complicated distribution, that is, I have a very long thread, I will simply cut it into pieces. I will simply take one, I will say, this is the electric charge over it, yes, and this is the length or the area or the volume, and okay, this is like this. I will sum it over all things and your problem is done. Similarly, when we have the case of you say some fluids, for example, if you have got a pipe like this, you want to say, okay, this much water is coming out of it, right? So, what is the amount or what is the density or how much amount of water is contained in this tube? Means you want to know about per second or per minute or per hour how much water is coming out of it, or how much water this pipe or this tube is able to hold. It is exactly the same. I will simply divide it into some compartments, this compartment, this compartment and this compartment. I will say it is having this much, and since these three are equal, I will simply sum it up and I will get, oh, so this much amount of water is there in the tube. It looks really very easy now. That is the beauty of physics. You can simplify everything and you can create the analogy, but in creating the analogies and simplify everything, the beauty of physics and the interest of physics remains the same. So now let us come to what we have discussed today. Actually, we have discussed two of very important concepts in the field of electrostatics. We started by revising what exactly are electric dipoles, how do they behave, what is the torque acting over when they are placed in electric field, what is the importance of the notion of the dipoles, how do they behave with some point P where a test charge has been put. And then we said, okay, we have got some discrete charges, but we must also take into consideration the continuous charge distribution. In the continuous charge distribution, we discussed about three other things. We went for the linear charge distribution, then we said there is some what we call spherical charge distribution, that is what we call the volume charge distribution also, if you take a sphere in place of a cube. And we also have a surface charge distribution, where we take some 2D objects like a square sheet or some sort of planar things, and then we try to find out the charge densities due to them. We also linked the charge densities with the electric flux due to some point charge and the cross sectional area that comes into contact with it. And we also had an analogy with the concept of mass, that we can divide any body of say suppose mass m into some smaller masses m1, m2, m3, and then we find out the properties of some mass say m1, and then we will integrate it to all the masses. Same that we can apply in the continuous charge over distribution, finding one, integrating all. We also found out that the continuous charge over distribution can also be seen as the property of fluids. The total amount of water coming out of a fluid, we can divide it into equal parts, and then we will have the amount of total water contained in that cube. Thank you.